I just finished the fall exam for 2019 for MA262, and I'm hopping right in to the spring 2019 exam for the same class. So yeah, let's go. We're finding y of x as the solution to this initial value problem. Well, it's not immediately obvious what we're supposed to be doing here, but if we divide out an x from everything, it's always a good idea to get rid of any terms that are on your highest term derivative. We get y prime plus 1 over x times y is equal to 3x plus 2 minus 4 over x. And this is in a form that we're much happier with because we have some function of x on this right side. We will call this q of x. We have some function of x multiplied by this y. We'll call this p of x. And the coefficient on y prime is 1. So this is a perfect case, and we're perfectly set up right now to do integrating factor. So integrating factor says that rho of t, which is our integrating factor, is e to the integral of p of t. Well, we're not dealing with t, we're dealing with x. I'll replace that. So we get e to the ln x, which simplifies down to just x. And integrating factor, the method overall says that y of x then is equal to 1 over rho of x times the integral of rho of x multiplied by q of x, our right-hand side. That's 3x plus 2 minus 4 over x dx. We can rewrite this integrand as 3x squared plus 2x minus 4 dx, and say that y of x is equal to 1 over x multiplied by x cubed plus x squared minus 4x plus c. We're told that y at 1 is equal to 0. That's equal to 1 over 1 multiplied by 1 plus 1 minus 4 plus c. So this becomes negative 2 in here. And if all of this is to evaluate to 0, this whole right side evaluates to 0, then c has to be 2. So we'll replace that in there. And what are we searching for in the end? We're looking for y at 2. Y at 2 is equal to 1/2 times 8 plus 4 minus 8 plus 2. That gives us 3. So 1 is C. 2, y of x is the solution to this initial value problem. We're looking for y at 2. So is this equation separable? It does not look like it is. Is this equation exact? Also don't think so. So what we can probably do here is apply, because we have this big kind of quotient on the right side, we can apply the substitution y over x is equal to v, and dy dx is equal to dv dx times x plus v. So let's do that. We have dv dx times x plus v is equal to, and if we divide this numerator by x, and we divide the denominator by x, that's perfectly legal, and we will be left with 4v minus 3 over 1. Okay, that's pretty perfect. That simplifies out nicely. So what can we do now? We'll subtract this v from that side. We have 3v minus 3 now, and we are ready to integrate, or we're ready to separate our variables. It looks like they're pretty separated now. Let's multiply 1 over dv over to this side, and then what we can do is flip the numerators and denominators of each side, and I'll actually bring this over here too. We'll be left with 1 over 3 times v minus 1, and that's equal to dv, and that's equal to 1 over x dx. We'll integrate both sides. We will get 1/3 ln v minus 1, that's equal to ln x. Okay. This is going to be a little interesting putting this into the correct form. We'll take e raised to the power of both sides. We can simplify things out a little bit that way. That gives us v minus 1 to the 1/3 power is equal to x. And oh, I almost missed it. This right-hand side will be, when we evaluate this, will be ln x plus c. So this is ln x plus c. We can bring this c down here, so we end up with cx over there. Okay, let's undo our substitution. We have y over x here. Let's cube both sides. Y over x minus 1 is equal to c, just some other c, cx cubed plus 1, and we'll multiply our x over. And that, theoretically, if I did everything right, is our solution. So we can apply this initial condition. Y at 1 is equal to 2. So that means that c is 1. And we can solve for y at 2. Y at 2 is going to be 2 to the 4th power, which is 16, plus 2, which gives us 18. So 2 is a. And I'm surprising myself. Yeah, that is correct according to the answer key. Okay, this is looking extremely exact. Hopefully you can tell what I'm looking at to see that. We see some kind of similar terms going on here, and they even have it parenthesed off for us. We can call this term m, and this term attached to dy dx n. If my is equal to nx, then our equation is exact. My is e to the x, well, it's the partial derivative of m with respect to y, e to the x cosine y minus 1, and we'll see if that's equal to nx, which is e to the x cosine y minus 1. So yep, we are dealing with an exact equation here, and all we need to do is take the integral of m dx and compare it with the integral of n dy. So the integral of m dx will give us e to the x sine y minus x squared minus xy, and let's compare the terms that we found from that with the integral of n dy. That gives us e to the x sine y minus xy minus y cubed. Okay, so now what we have here is two expressions that we can form our solution from. So since we have overlap in all of the terms that contain both x's and y's, here we go, we'll only count those guys once, so we're left with a solution e to the x sine y minus xy minus x squared minus y cubed, because we still have these unique terms that we have to count additionally, is equal to some constant c. We're told that y at 0 is equal to pi. So let's solve for that. This term will go to 0. We will have, oh yeah, and so will this one, and so will this one, but this one will be this guy right here will be negative pi cubed. Did I mess up my, oh yeah, look at that. How did it looks like I integrated n dy and got minus y cubed. That should be a plus. There we go. So applying our initial condition, we end up with pi cubed over there. And that is our answer, which is option E for number 3. We have a container with 10 liters of water, blah, blah, blah. This is just one of our salt tank application problems. Our equation for this is dq dt plus r0 over v of t times q is equal to ri ci. Let's start putting some of these or plugging some of these values in. So R0 is the rate at which our fully mixed solution is flowing out of our tank, and we're told that that is at a rate of 1 liter per minute. Then we know that salt solution is pumped into our tank at a rate of 2 liters per minute, so I'll replace that Ri with a 2, and the concentration that's pumped in is 4 grams per liter, so we get 6 over here. So you can't tell, but I just did an entire take going through the entire rest of the problem before realizing that my answer is wrong, not because I made some mistake in my integration or anything expected like that. No, and you just saw it happen. I just multiplied 2 and 4 together and got 6. Yeah, no, this would be 8. So now we can continue. So if we're doing integrating factor, P of t is just this coefficient on Q here, 1 over 10 plus t. Rho of t is e to the integral of P of t dt, which will be ln 10 plus t, which we can just rewrite as 10 plus t. And so we can say that Q as a function of t is equal to 1 over rho of t times the integral of rho of t multiplied by Q of t, which is just this 8 here. So we get 80 plus 8t dt. This becomes 80t plus 4t squared plus c. We are told, oh, and I forgot to erase that, we're told that our initial amount of salt in the tank in grams is 20 at t is equal to 0. So 20 is equal to 1/10 multiplied by c. So c must be 200. There we go. Okay, so we're looking for the concentration of salt in the tank at 10 minutes. For that, we will need to know the total amount of salt in the tank at 10 minutes and the volume. So grams at 10 minutes and liters at 10. So we're solving for those two. So finding grams at 10, we're just finding Q at 10. That is equal to 1 over 20 multiplied by 800 plus 400 plus 200. So that gives us 1400 over 20, 1400 over 20, which is 70. And so our grams at t is equal to 10 is 70, but what is our liters? Well, this is our function, our volume as a function of time. If we plug in 10 to that, we get 20 liters. And so our concentration is our grams divided by our liters, so that gives us 3.5, so 4 is C. Okay, question 5. We are considering this equation here, and we're performing a substitution v equals y squared, and we're figuring out what that substituted equation turns into. So this is actually a Bernoulli equation where we have y prime plus p of x times y is equal to q, that's a g, q of x times y to the nth power. And in our case, that n is equal to -1. And what we do for Bernoulli equations is perform a substitution here, and I'm just reading off of a page for Bernoulli equations. This is a little bit hard to remember off the top of your head, but here it is. V, our substitution is v is equal to y to the 1 minus n, and since n is -1, we get y squared. So this is just the same Bernoulli substitution that we would be performing to solve this equation anyway. And what we also know is that v prime, or dv dx, will be equal to 1 minus n times y to the -n times y prime. This 1 minus n will give us 2, y to the -n will give us y to the first, and if we divide that 2y over, we can replace our y prime up here with that. So we have dv dx times 1 over 2y plus, let's see, 1 over Actually, I think it's a little sketchy. I'm kind of half substituting all at once, so I'll just keep going by this page that I'm reading. This is just like Paul's online math notes, which are very, very useful for this kind of thing. But in the end, if you just want to memorize this equation, we get, after all of our substitutions, we get 1 over 1 minus n times v prime plus p of x v is equal to q of x. And that's actually pretty easy to remember right there. So this 1 over 1 minus n will give us 1/2. I'll replace this with not dy, dv dx. Our p of x is just this original term over here, and so is this q of x, but note that it will be only the function of x, so we get e to the x here and 1 over x. Whoops, 1 over x there, and then if I go back to our answer choices, if we multiply this 2 up into everything, I think we should have one of these choices. Exactly. Okay, I'm seeing D. Is 5D? Yes, it is. Okay. Yeah, you very rarely have to actually deal with these things. This is the only time I've seen a Bernoulli equation come up in 266, 265, 266 or 262 on a final. But that said, I'm not really familiar with the 262 finals, so don't take that for much. Okay, we have a linear system of equations here. Which of the following statements is true? So we're dealing with whether this system is consistent, inconsistent, or has infinitely many solutions. Let's just put this into augmented matrix form. We have 1x minus 1y plus 1z is equal to 2, 1, 4, 2, 2, and 2, 3, a squared minus 1, and a plus 2. Okay, well, I think some interesting things are going to happen if we subtract row 2 from row 3. That will give us a 1 here, a negative 1 here, a minus 3 there, and an a there. And we see that in order for this system to be consistent, we have these two guys. These two guys are equal, but actually no, this isn't necessarily an issue for us just yet. But it's a good start. So let's see. We should be able to plug some answer choices in here to be able to figure some things out. So A says if a is equal to negative 2, then the system is consistent. Let's see, if we plug in negative 2 here, we will end up with 1 here and negative 2. And no, that's not looking too good because we have the same combination of x, y, and z here and here, but they're equal to 2 different things on the right-hand side. So that's no good. Our system is inconsistent. Let's just jump around here a little bit. Let's go to E. If a is equal to 2, then the system has infinitely many solutions. And I'm going here for a reason, because if we plug in a equals 2, we'll get 1 here, but we won't get negative 2 over here. We will get positive 2. And what we'll be able to do is use row 1 to set row 3 equal to all zeros. That means that x3 will not have a pivot position in here, and so we'll have a free variable, and we'll have infinitely many solutions as a result. So this does end up being true, and you can test all these other ones. You won't really find much, but what my philosophy with these problems where you got a big kind of crappy system to deal with, don't focus on simplifying the thing all the way down, because really it's just about getting it to a point where you've just made it a little bit easier for yourself to test through all of the answer choices. So 6 is E. Oh god, okay, the Wronskian of these functions is what? So the Wronskian, if these are f, g, and h, is going to be the determinant of f, g, h, f prime, g prime, h prime, f double prime, g double prime, h double prime. This is not going to be particularly fun. Okay, let's just start filling all these guys in. We have x, 1, 0. sine x, cosine x, negative sine x, cosine x, negative sine x, negative cosine x. Okay, okay, this is going to be great. So we can write this determinant as x times the determinant of this submatrix, which is just formed by crossing out x's row and column, and then we will subtract 1 multiplied by the determinant of this submatrix, and then really we're adding 0 times the determinant of this submatrix, but that will just evaluate to 0, so we don't really care about what's going on there. So we have x times cosine x, negative sine x, negative cosine x, negative sine x, and minus 1 times sine x, cosine x, negative sine x, negative cosine x. Let's find all of these guys. We are going to get here we'll get x multiplied by negative cosine squared minus sine squared. So that will be x times 1, and then we'll have negative 1 times, oh, that works out nicely. We will have negative sine times cosine, and here we will have positive sine times cosine. So all of that will go to 0. So we are left with x times 1. So our answer for 7 is, ooh, wait. No, I'm sorry about that. That's a stupid mistake. When we find this determinant, we get negative cosine x squared minus sine x squared. And so we can factor out a negative 1, make this a plus, and then all of this will simplify down to 1. So there we go, we have negative x. Sorry about that. Ugh. Okay, let's find the basis for the null space of A. Let's just row reduce this thing and make, looks like it's going to end up being 2 vectors out of our free variables. So 1, negative 2, 2, 3, 2, negative 4, 5, 7, 3, negative 6, 3, 6. I'll turn this row into 1, negative 2, 1, 2 for now. And let's take row 1 and subtract it from row 3. That gives us 0, 0, minus 1, minus 1. This can become a 1, 1. I'm just speeding through this a little bit. We can turn this 5, 7 into a 0, 2, this into a 0, 1. And then would you look at that? Row 1 is a multiple of row 2 and vice versa. If we multiply row 1 by 2 and subtract it from row 2, we will get an entire row of zeros here. So there we go. If I rearrange this a little bit into echelon form, we have, well actually it's reduced echelon form, we have our row reduced version of A, which is awesome. Let's write these out in equations. We have x1 minus 2 x2 plus x4 is equal to 0, and x3 plus x4 is equal to 0. Let's move all of our free variables, which in this case is x2 and x4, because they don't have, their columns don't have pivot positions. We have only a pivot position in column 1 and column 3. But let's move all those free variables over to the other side. We have negative x4 minus x4 to x2. Okay, so if we are making an x2 vector and an x4 vector, really we're answering the question, how many x2s is x1 equal to? It's equal to, not x, it's equal to 2. We have x1 equal to 2x2. Then x2 is equal to 1 x2 because it's equal to 1 of itself, and then it's not dependent on x3 or x4. Then for x4, x1 is equal to negative 1 x4. It's not dependent on our other free variable. It's equal to negative 1 x3 and 1 of itself. So 2, 1, 0, 0, and we can flip all the signs on x4, and we'll still have the same vector. It'll still have the same span. So C is our answer for, what is this, 8? Yep, C. Okay, kind of scary determinant, except it's not that scary for number 9. Let's write down this little tool that'll help us in a second. Plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus. Okay, so how are we going to use this? Well, if we have something like this 3 or this 2, an element that's in a row or a column all by itself, what we can do is kind of pull that outside of our matrix, but we have to make sure that it comes out with the sign associated with it from this matrix. So we can pull that out and then multiply it by the determinant of the matrix that we get by crossing out its row and column. So we're going to do that with this 2 here. That 2 will have a negative sign coming from that matrix. So we have negative 2 multiplied by a 3 by 3 determinant instead of a 4 by 4 determinant. That's 1, 2, 4, 0, 1, 2, 0, 0, 3. And I'll also shrink this guy. You'll see why in just a second. So now I don't really feel like taking a 3 by 3 determinant. So let's pull out this 3 because it's in a row by itself with all zeros. It'll have a positive sign on it. So we can rewrite this as negative 6 multiplied by a 2 by 2 determinant where we just cross out the row and the column that had that 3 in it. We have 1, 1, 0, 2. This gives us negative 6, so 9 is A. 10, we have a transformation from P2 to R2. It's linear and it satisfies these properties. Okay, great. So by the properties of linear transformations, we know that if we can find the linear combination of this input vector and this input vector and this input vector that gives us x squared, then all we'll have to do is take the same linear combination of the output vectors, and we will have the output. And this is going off of the property of transformations, that the transformation of x1 plus x2 is equal to the transformation of x1 plus the transformation of x2, and also the property that the transformation of c times x is equal to c times the transformation of x. So really we're just applying these behind the scenes, but you don't really particularly need to know that those exist. Like we're using them in the background. That's about it. Okay, so it's a little difficult taking linear combinations of polynomials while they're in polynomial form. So let's make vectors out of all these. So we'll have a vector with an x squared position, an x position, and a constant position. So this first input vector would be 1, 1, 0. This second input vector will be 0, 2, 1. And this third would be 0, 0, 2. And we're finding the linear combination of these that gives us 1, 0, 0 because we just want an x squared. So let's subtract row 1 from row 2, like that, and then subtract row 2 from row 3. There we go. So we see that we need one of these guys. So I'll just skip straight to solving this thing, because we said that whatever linear combination we get here, we're just taking the same linear combinations of the output vectors. So we have 1 times 1, 0, minus 1/2 times 1, 1, minus 1/2 times 1, 1, and then plus 1/4 times 2, negative 2. Okay, so this is 1, 0, or I'll just directly solve for it, sorry. We will get our top position will be 1 minus 1/2 plus 1/2. So that's just 1. And then on the bottom here, we will have negative 1/2 minus 1/2. That's negative 1. So E is our answer for 10. 11, we have a matrix A. Given that the determinant of A is 3, find the 1, 2 entry of A inverse. Well, every single entry of A inverse will be multiplied by 1 over the determinant of A. So we have 1 over 3. And what is the 1, 2 entry of A inverse? Well, that's going to be the 2, 1 cofactor of A. So the 2, 1 cofactor is, let's see, that's this position in our matrix. That's going to be the determinant of the matrix that we get by crossing out the row and column that 2 is in. That gives us 1, 4, 1, 1. That gives us, let's see, that gives us negative 1. But then if we were to evaluate this, we would get negative 1 at this point. But what we have to remember, just to add another layer of complexity, is that every single entry of A inverse has a sign on it if we're doing this cofactor expansion, but it's something that we've already seen in this video. It's just given by this plus minus plus scheme here. So the 2, 1 entry will have a negative sign, so we can add that there. This determinant becomes negative 3. So we get 1, which is D for number 11. Which of the following are vector spaces? Ooh, this is an interesting one, because in MA 265 and 266 we never deal with these kind of things, differential equations as vector spaces. But this is kind of cool, so I think we can work through this fine. But let's start with number 1. So all of the points in R2 such that x is greater than y. So here's the line x equals y. Which side of this has all the values such that x is greater than y? Well, it's down here, right? If we take this point here, its x component is greater than its y component. But it's important to note that this set extends infinitely all the way down here, but it doesn't include this line itself, which is an issue right off the bat, and it can let us just completely throw this one out. Because what about 0, 0? 0 is not greater than 0, so the origin is not included in this subspace, and as a result, this guy cannot be, sorry, I said subspace, I meant vector space. This guy cannot be a vector space. What about 2? We have all the x and y's in R2 such that 2x minus 3y is equal to 0. So that's just going to be, I'm not drawing this accurately here, but that is just a line that passes through our origin, and you can go check through all of the different things that we care about for subspaces, or sorry, vector, I keep doing that, because most of the questions in MA 265 are actually about subspaces, not vector spaces, so I'm a little thrown off here, but we get a line through the origin, which is one of the things that we like to see in finding vector spaces and subspaces. And this guy will be closed under vector addition, closed under scalar multiplication. You can express it as a span, and so it works perfectly well as a vector space. Okay, what about 3? All solutions to this guy on negative infinity to infinity. Well, let's find our solution. This characteristic equation is r squared plus 2 is equal to 0. R is equal to plus or minus root 2i, and so y is equal to c1 times cosine root 2t plus c2 times cosine, times sine root 2 times sine root 2t. So we have our solution here for y, for option 3, and we're kind of trying to think about whether or not this satisfies all of our rules for a vector space. So is it closed under vector addition? Well, if you take some C1 cosine 2t and some C2 sine 2t, and then you change those C1s and C2s and you add them together, yeah, you'll get something else that's just another entry or another member of our vector space. If you multiply this by some constant, you'll still be good. This includes the origin, the 0 element. Yeah, no, this seems pretty good. This seems pretty good to me. So we're going to give this a tentative check mark, but we're still between B and C. So let's solve number 4 here. We can rewrite this as y double prime is equal to -2, so y prime is equal to -2t plus c, and then y is equal to -t squared plus ct plus d. Okay, well, there are immediate problems here. If we take two elements of the set and add them together, let's say a C1 and a C2 and a D1 and a D2, we can get another entry, hopefully, of our set. We will have -2t squared plus C1 plus C2 times t plus D1 plus D2. And this is not good. This is not good at all, because no matter what, -2 is not equal to this -1, which all of our entries, I keep saying entries, all of the members of our set have to have. We have to have -t squared. But when we add elements, we get -2t squared. So this is not closed under vector addition. And so there we have it. We have answer choice C for number 12, because 4 does not work. If you're perceptive, you might have noticed that the date in the upper left corner just changed from what would it have been, Monday May 11th to Tuesday May 12th. That's because I messed up my explanation for this one yesterday, so I have to go back and fix that now. So we're looking for vectors that form a basis for this span. So first things first, since we're really looking for the basis for the column space of the matrix formed by smushing all these vectors together, let's figure out what the row reduced form of this is. 2, 0, 1, 1, 3, 1, 1, 2, 4, 0, 2, 2. And I'll change this to a 2, 0, 1, 1. There. Okay, let's subtract 2 row 1s from row 2. We get a 0 here, a -2, and a -1. Let's subtract 3 row 1s from row 3. That gives us a 0 here, a -2, and a -1. You're noticing a pattern here. We can set this to all zeros using row 2. And let's subtract 2 row 1s from row 4. We get 0, -2, and who would have guessed? -1. So yet again, we can use row 2 to set this row to all zeros. There we go. Okay, so really all we need to know for finding a basis for our column space is which rows have pivot positions in them. So because which columns have pivots in them. So because column 1 and column 2 are pivot columns, those will most definitely form a basis for our column space. So in the end, since we only have 2 pivots, we know that we're looking for an answer choice that has only 2 vectors in it. And additionally, because we don't have, since we have 2 pivots, you have 2 pivots here and no pivots here, essentially what this is going to look like is we're kind of spanning the xy plane in this 4-dimensional space. But okay, so now here's the issue. Take a look at the only answer choice that only has 2 vectors. These are not the 2 vectors. These are not the 2 vectors that we've picked, which is a big issue for us. Well, or so it seemed. So it seemed to me yesterday. But the thing is, what will happen if we reorder our vectors, and instead of 1, 2, 3, 4 being first, what if we switch it with 1, 1, 2, 2? Well, then our reduced echelon form will just look like this. And so you see actually we'll have to we'll have to do a little messing with it. Let's add row 1 to row 2 to get a 0 here, a -1, -1 here, and a 1 here. But you see, we still get a perfectly valid, reduced echelon form where we have the same pivots. This is still spanning all of, not all of R2 because we're in 4 dimensions. We can't really call it R2, but it's, we have things spanning the XY plane, which is exactly what we're looking for. So this is just a slightly different basis for our column space, but still a perfectly valid one. Sometimes they will kind of pull that on you, but you could have just skipped all that work by just trusting yourself with your row reduction and saying, okay, well, we know that our answer has to have only 2 vectors in it because we only have 2 pivots in our reduced echelon form, and so we'll just go with D anyway. 14, given that A and B are 4x4 matrices, the determinant of A is 2, and the determinant of all that is 1. We're finding the determinant of B. Okay, time to apply some properties. We know that the determinant of AB is equal to the determinant of A multiplied by the determinant of B. So we can use that fact, and also the fact that the determinant of A inverse is equal to 1 over the determinant of A, and that in general the determinant of A to the okay, well actually we'll calm down for a second and just apply those 2 just to start off with. So we can rewrite this as 1 over, let's see, actually will it be 2 over? Okay, we actually need more rules, sorry. We know that the determinant of Ka, where K is some constant, is equal to K to the n times the determinant of A, where n is the number of rows or columns in our matrix, so that in our case will be 4. Okay, let's start rewriting things. The determinant of 2a to the negative second power times the determinant of B transpose is equal to 1. I'm just applying that first rule that I wrote out and then erased. We know that the determinant of A transpose is always equal to the determinant of A, and so that applies for B as well. This is just the determinant of B, and this is actually kind of nice. We can divide this whole determinant out, and what will we get? We'll have 1 over the determinant of 2a to the negative second power. We know that 2 times a to the negative second power will just be equal to the same thing if we pull out a 2 and raise it to the 4th power, where 4 is the dimension of our matrix. So we have 1 over 16 over here. Now the determinant of a to the, and I'll remove this over here, a to the negative second power. That's just the determinant of a to the negative first power times the determinant of a to the negative first power. We know that each of these individually is just 1 over the determinant of a, so overall we will get the determinant of a multiplied by the determinant of a up there. Since the determinant of a is 2, we have 4 on top and 16 on the bottom, so 14 is b. The determinant of b is 1/4. Sorry, that was a little sloppy on my part. 15, for this equation, we're finding yp, our particular solution. So how are we going to do that? Well, we're going to do that with undetermined coefficients here, but it looks like we are going to run into a little bit of an issue. So let's first find our characteristic solution and what we would like our guess for y particular to be. Well, our guess for y particular, we'd like that to be a generalized form of 2 e to the t, that's a e to the t. But if we pull out our characteristic equation, r squared plus r minus 2 is equal to 0, this factors to r plus 2, r minus 1 is equal to 0. We see that r is equal to 1 is a solution, so yc is equal to c1 e to the negative 2t plus c2 e to the t. As a result, sadly, we have to multiply this guy by t to avoid that overlap there. All this means is that our differentiation just got a little bit more complicated. So I'm going to remove this guy because all we're looking for is our particular solution here, and we will find a couple derivatives. Y prime will be a e to the t plus at e to the t, and y double prime will be 2a e to the t plus at e to the t. We can plug these in for y double prime, y, and set that equal to 2e to the t. But if you take a look, every single term has an e to the t in it. So I'll just remove all of those. We have 2a plus at, that's our y double prime, plus a plus at, that's our y prime, minus 2 multiplied by y, that's just at, and that's equal to 2, and I'm removing that e to the t. So overall, we have 2a plus a, that's 3a, and then we have an a to the t, an a to the t, and a minus 2a to the t, so that all becomes 0, and we get that is just equal to 2. So a is 2/3, and so this isn't our guess anymore, this is just y particular, our particular solution, that's 2/3 t e to the t, so 15 is e. Let A be the matrix defined here. Count the number of true state, yuck, I don't like this. Okay, count the number of true statements about A among these. So the vector 103 is an eigenvector with the eigenvalue lambda equals 2. Well, we can check that really quickly. If I just write out A, we know that an eigenvector, when multiplied by our matrix, will just be scaled by whatever eigenvalue is associated with it. So if we compute this, we get 2, negative 3 plus 3 is negative, wait, really? No, it's 0. I can't, math's pretty hard. 0. And then 6 here. So yes, this is true. The amount that we've scaled this vector to get this guy is 2. So the eigenvalue associated with this vector is 2. That checks out. 1 plus I and 1 minus I are eigenvalues of A. That's looking a little sketchy. We're going to go test option 3 first. Yeah, I don't really feel like figuring all of that out, because if we know that negative 1 and 4 are eigenvalues of A, since at max we can have n distinct eigenvalues, we will know that this guy is not true. So we'll plug in negative lambda to a minus lambda I. Sorry, we'll plug in lambda, not negative lambda. So we get negative 1 minus lambda, 0, 1, negative 3, 4 minus lambda, 1, and 0, 0, 2 minus lambda. We can rewrite, this is, we're finding the determinant of this and setting it equal to 0. We can rewrite this determinant as 2 minus lambda multiplied by the determinant that we get by crossing out the row and the column that 2 minus lambda is in. So 2 minus lambda multiplied by this 2 by 2 determinant, negative 1 minus lambda times 4 minus lambda, negative 3, 0. This gives us 2 minus lambda times negative 1 minus lambda times 4 minus lambda is equal to 0. So this has roots lambda is equal to 2, 1, and negative 4. Ooh, interesting. Actually, wait, I'm I'm bad at this. This is -1 and +4. There we go. Whoopsies. Um, yeah. Okay. Sorry about that. God. Okay, there we go. So that tells us that 3 is correct, that -1 and 4 are eigenvalues of A, and that because A is a 3 by 3 matrix, it can't have, more than 3 eigenvalues. Also, we found all of our eigenvalues here, so these two are definitely not eigenvalues. And let's figure out 4. A has 3 linearly independent eigenvectors. Well, since we have three distinct eigenvalues, we are going to have, by definition, 3 linearly independent eigenvectors. Just like how an n by n matrix with n distinct eigenvalues is always diagonalizable because all of its eigenvectors will always be. Wait, you guys don't even do diagonalization, I think. Okay, sorry to confuse you if that was confusing. But no, all of our eigenvectors will be linearly independent because they come from different eigenvalues. So we have 3 correct statements here, and 16 is D. 17. Okay, we are finding 2 times the dimension of null A minus the rank of A. Interesting. What kind of annoys me is that most of the time you see it written as NUL instead of NULL, but we're not gonna care about that. Okay, let's row reduce this matrix. That's pretty much all the work that we need to do for this problem. 1, 8, -3. Okay, let's subtract row 1 from row 3. This can become 3 and -2, and we can use row 2 to set this to zeros. So we're in pretty much echelon form here. We see we have 2 pivots. That means that our rank is equal to 2, and given our equation that nullity plus rank, which we know is 2, is equal to our number of columns, which is 3, nullity must be 1. Where nullity is just the dimension of the null space of A. So 2 times that is 2, minus our rank of A, which is 2. That gives us 0, so 17 is B. Okay, variation of parameters looks like the general solution to this homogeneous equation on that interval is given there, and blah blah blah. We're trying to find some very particular things here. We're finding u1 prime and u2 prime, where u1 of t is the thing multiplied by t to the -1st power, and likewise for u2. So we need to write out the entire equation for variation of parameters, and you'll be able to see how this question is actually a lot easier than most of the variation of parameters questions that they can throw at us. We know that y of t by variation of parameters is -y1 times the integral of y2 times f of t over the Wronskian dt plus y2 times the integral of y1 times f of t over the Wronskian dt. So we need these 4 values here: y1, y2, f of t, and the Wronskian. But importantly, we are looking for, so u1 of t and u2 of t. Where do those come from? Well, they're just the things multiplied by our first fundamental solution and our second fundamental solution. I'll just note those there: t to the -1st and t to the -5th. So if we factor a -1 in here, here we go. Here is u1, here is u2. They're the things multiplied by y1 and y2, and when added together give us our solution. But the nice thing is we're not looking for this whole integral. We're looking for the derivative of these guys. And that will cancel out both of these integrals. So u1 prime is just that thing, and u2 prime is just that thing. So let's find f of t and our Wronskian, and we should be able to solve for these guys. Now f of t is the thing on the right-hand side of our equation, so that whatever is not connected with any y's or any of its derivatives, any derivatives of y, so long as the coefficient on our highest derivative, y double prime, is 1. So if we divide t squared out there and t squared from there, we see that f of t is 1 over t. Now finally, our Wronskian is the determinant of the matrix formed by our fundamental solutions, t to the negative first, t to the negative fifth, and their first derivatives. So negative t to the negative 2 and negative 5t to the negative 6. This gives us negative 5t to the negative 7 plus t to the negative 7. That's negative 4t to the negative 7. So let's go in here and replace everything. Minus 4t to the negative 7, minus 4t to the negative 7. Our f of t's will become t to the negative firsts. This negative y2 will become negative t to the negative 5. This y1 will become t to the negative 1. And we seem to be good to go here. Yeah, okay, I think we're good. Let's get rid of those. We will have t to the 7th on the top and t to the 6th on the bottom. So this will just give us t over 4 there, and that gives us our answer choice. 18 is A, but then over here we get t to the negative 2 and t to the negative 7 on the bottom, so we'll get t to the 5th over negative 4. And that is exactly what 18, option A, is telling us. Okay, 19, a spring mass system is given by this initial value problem here, where t is the number of seconds after motion begins. How many seconds does it take the mass to cross its equilibrium position for the first time? Okay, so we need to find a general solution. Here we'll pull out our characteristic equation. R squared plus 3r plus 2 is equal to 0. Can we really factor this? Let's see, r plus 2, r plus 1 is equal to 0. That looks like it works to me. It's hilarious that I'm second guessing the factoring out of everything, but no, that looks good. So r is equal to negative 2 and negative 1. As a result, we can find y of t. That's just c1 e to the negative 2t plus c2 e to the negative t. We're told that y at 0 is equal to 2 and y prime at 0 is equal to negative 5, but in order to apply that, we'll need y prime of t. That's negative 2 c1 e to the negative 2t minus c2 e to the negative t. And let's plug in t is equal to 0. So 2 will be equal to c1 plus c2, and negative 5 will be equal to negative 2 c1 minus c2. We can make this into an augmented matrix. 1 c1 plus 1 c2 is equal to 2, and negative 2 c1 minus 1 c2 is equal to negative 5. Let's solve this. Flipping all those signs, let's subtract 2 row 1s from row 2. We get 0, negative 1, and 1. So c2 is equal to negative 1, and we can subtract this here and see that c1 is equal to 3. So y of t is equal to 3 e to the negative 2t minus e to the negative t. We are trying to find how many seconds it takes for our mass to cross back to its equilibrium position. So that will be the case when y of t is equal to 0. because that should be our equilibrium. So solving for t, 0 is equal to 3e to the negative 2t minus e to the negative t. And from this point, you can really solve for t however you want. I tried to go do it, and it was whatever I was doing was not a very good way of going about it. But worst comes to worst, we would expect our answer to involve some e's in some way. Sorry, not e's, natural logs in some way. So these answers are really the only three we're thinking about plugging in. And since we have a 3 running around here, might as well just try plugging b in. And sorry, because this one definitely does work, so I'm not just picking it for no reason. That'll be 3e to the negative 2 ln 3 minus e to the negative ln 3. We can rewrite these 3 to the negative 1 here, and 3 times, come on, times 3 to the negative 2 there. Well, 3 times 3 to the negative 2, that's just 3 to the negative 1. Subtract 3 to the negative 1 from that, you get 0. So this guy does work perfectly. So 19 is b. Given that the function y1 of t is the solution to this differential equation, we are doing blah, 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 reduction of order, finding the second fundamental solution here. So reduction of order says that y2 of t is equal to y1 multiplied by the integral of e to the negative integral of p of t dt over y1 squared dt, where p of t is whatever function of t is connected to y prime, so long as the coefficient on y double prime is 1. So we'll divide everything by t squared, and so we'll see that the function of t on y prime is 2 over t. This gives us negative 2 ln t up here, or just t to the negative second power. Now y1 we're told is t, so we'll get a t here and a t squared. So at this point we can solve things. This integrand will become 1 over t to the fourth, so we can say that y2 of t is equal to t multiplied by negative 1/3 t to the negative 3 plus c. Okay, great. So we can expand this out. y2 of t is equal to negative 1/3 t to the negative 2 plus c times t. And so really, whatever coefficients are on here, they don't matter at all. The only thing that matters is that we have a t to the negative 2 term and a t term. And c works perfectly for that. So 20 is c. Okay, this looks a little scary. General solution to this equation right here is what? Let's hope the answer is A or B. It is not. Okay, general solution. So let's figure out, if we pull this guy out as our characteristic equation, r squared times r squared minus 8r plus 25 squared is equal to 0. Let's try to figure out what all of our roots are here. This is going to be a whole lot of fun. So right off the bat, we can just see that this r squared will give us r equals 0 with a multiplicity of 2. So that's fine. But then what about the rest of this? We will, I think we're going to have to use, we're going to use the quadratic formula. Negative b, so that's 8, over 2 plus or minus the square root of b squared minus 4 times a times c, that's just minus 100. And would you look at that, that gives us minus 36 in here, minus 36, and that gives us 6i. We can simplify that down to 4 plus or minus 3i with this whole thing has a multiplicity of 2, and that's our other solution. Okay, so we'll go manually write out our solution here. Y of t is equal to, well, what's this 0 with a multiplicity of 2 going to do? That's going to give us, I don't like writing c's with subscripts, so we're going to use a's and b's, etc. A plus bt, that's what we'll get there. And then it gets a little more complicated, plus c e to the 4t cosine 3t plus d e to the 4t sine 3t plus e to the 4t times t cosine 3t plus f e to the 3t times t sine 3t. Yeah, so that's it. And that's D. Yeah, that's a little crazy. But again, you kind of saw that wasn't actually too bad. So don't get too discouraged when you see how many components is this? 6 in an answer like this? Yeah, oftentimes it's a little more straightforward. You just have to be careful to not, for example, pick the one with the negative 4 x's instead of the. Also, I switched to, yeah, they're using x. Whatever, doesn't matter. 22. If we're using undetermined coefficients to find a particular solution here, what form will it have? Let's find the two things that we always go for here. Y pg, our guess for y particular as a function of x. So this is what we would like our guess for y particular of t to be if we didn't have any overlap with our characteristic solution. So that just generalizes what we have going on over here. So that's a e to the x plus bx squared plus cx plus d. Remember that we have to split any polynomial like this up into all of its lower powers, all the way down to the constants. So that's what we would like. That's what we would like to have happen. Now let's grab our yc as a function of x, our characteristic solution. Well, our characteristic equation will be r cubed minus r squared minus r plus 1 is equal to 0. Ew, they usually don't make us factor things like this. Yuck. I think I'm just gonna go test whether or not 1, negative 1, I, and negative I work for this. Actually, I and negative I wouldn't matter. The only thing we're really worried about is 0, which does not work, so we're good there. Yeah, this does not have a solution for r equals 0, but does it have a solution for r is equal to 1? We'll have 1 minus 1 minus 1 plus 1 is equal to 0, so that works. R equals 1 is definitely one of our solutions. That means that among the other components that yc could have, it will have a constant times e to the x, and then blah, 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 all the rest. We don't actually care about anything else, because the only other thing that could overlap with this solution that we have over here is if we had r equals 0, which would overlap with this constant. But in the end, we have overlap. We have overlap here. So we have some constant times e to the x and some constant times e to the x in both of these. So we will need to multiply this one in our guess by t, and that will give us our solution, which is b for 22. Oh no. Okay, well, I guess I'll just talk about why b is wrong then, because b is wrong, and it looks like it's wrong for a really rude reason. Okay, so turns out that r actually, sorry, r equals 1 actually has a multiplicity. Yeah, it's a helicopter, I think. R equals 1 has a multiplicity of 2, which means our answer is C. How, without factoring that, how do they want us to figure that out? I'm not sure. I really have absolutely no idea. Huh. Well, I guess this would have to be r minus 1 times r minus 1 times r plus 1, which would be r squared minus 2r plus 1 times r minus 1, which is, I can't believe I'm actually doing this, it's r cubed plus 2, what am I doing? R cubed minus r squared minus 2r, no, that's not even it. Okay, I don't know what to say here. I think unless I'm missing something major, you have to factor this thing in order to figure out that r equals 1 has a multiplicity of 2, because when it has a multiplicity of 2, we won't just get a c1 e to the x term, we will get a c2 x e to the x term additionally. So multiplying, and I said t too, multiplying this thing by x won't actually fix the problem. That'll just give us a new thing that we're overlapping with, so we need to multiply by x squared. I don't know what they're thinking with this whole thing. Am I crazy? R equals 1. How do we know that has a multiplicity of 2? I don't like that. I'm sorry about this. Yeah, that's not fun. Okay, 23. Which of the following is an annihilator of this function? So pretty much we're just looking for whichever expression over here has the roots that would lead us to get e to the x times x squared and then sine 3x. So that'll occur when we get what? We want r is equal to 1 with a multiplicity, the multiplicity of 3, right? Because that will give us a e to the x, an x e to the x, and a x squared e to the x. So r is equal to 1 with a multiplicity of 3 will do it, and r is equal to plus or minus 3i will give us a sine 3x and a cosine 3x. So which one of these works? Well, I kind of gave it away by circling 2 of them. Which one of these works for that? This will give us our solution for, in this case, d is equal to 1 with a multiplicity of 3, and here we just get d is equal to plus or minus 3i. So D is our answer for 23. And really just, I wish I had a better explanation for what the annihilator was. We did not talk about this term in MA266, which is interesting because usually in everything else we went like more into depth than you guys did in these problems. So I'm not really sure what to say here, but this tactic seems to work for these problems. You find whatever function in terms of D notation will give you this behavior over here. Question 24, let's find the solution to this initial value problem. Now we have x prime equals ax. We're going to use the eigenvalue method. We need the eigenvectors and eigenvalues of this matrix A. We'll be solving 1 minus lambda times 4 minus lambda plus 2 is equal to 0. Lambda squared minus 5 lambda plus 6 is equal to 0. Lambda is equal to negative 2. Sorry, lambda minus 2, lambda minus 3 is equal to 0. So lambda is equal to 2 and 3. For lambda is equal to 2, a minus lambda I will give us negative 1, 2, and 2, which simplifies down to 1, 1, 0, 0, giving us an eigenvector of negative 1, 1. For lambda is equal to 3, we will plug that into a minus lambda I and get negative 2, negative 1, 2, 1, which simplifies down to 2, 1, 0, 0, and we will get an eigenvector of negative 1, 2 out of that. Okay, great. We have our eigenvectors and eigenvalues. That means that we can write x of t as c1 times v1 e to the lambda 1t plus c2 times v2 e to the lambda 2t. And we can apply this initial condition here. X1 and x2 at 0 will be 4 and negative 1. That means that negative 4 1 is equal to c1 times negative 1 1 plus c2 times negative 1 2. We can make this into an augmented matrix. Negative 1 1 negative 1 2 is equal to negative 4 1. And I don't know, let's add row 2 to row 1. We get a 0 here, a 1 here, and a negative 3 there. Subtracting 2, I'm getting 7 right there. Okay, perfect. That tells us that C1 is equal to 7, so x of t is equal to 7 times negative 1, 1 e to the 2t plus c2. Well, c2 is negative 3, so negative 3, negative 1, 2 e to the 3t. We are finding x1 and x2 evaluated at 1. That will give us negative 7 e to the 2. So I'm getting b. Let's make sure that that checks out. Yep, 24 is b. So negative 7 e to the 2 plus 3 e to the 3, and then 7 e to the 2 minus 6 e to the 3. There's our answer. Perfect. 25, the fundamental matrix for x prime equals ax is given there. Thus, the general solution is what? So we know that this will have two components, and we're seeing this in all these answer choices where we have two components if we expanded this completely out. One of them will be C1 and C2 multiplied by this thing, because that will give us C1, and I'm just expanding this out by I, negative 1, 1 e to the negative t plus C2, 1, 2 e to the 5t. And that's just the form of a homogeneous, the form of a solution to the homogeneous system that we're used to here. And yeah, so we are expecting exactly what we see in the first half of all of these answer choices, where we have our fundamental matrix multiplied by C1 and C2 as a vector. So the kicker with this question is figuring out what our particular solution is. And instead of using x here for our fundamental matrix, I'm going to use capital phi, which is what I'm used to seeing from 266. We have an equation for this. Xp of t, our particular solution, is equal to our fundamental matrix multiplied by the integral of our fundamental matrices inverse, still evaluated at t, multiplied by g of t dt, where g of t is just this non-homogeneous bit over here. So that's going to be 12 e to the t and 0. And we know what this fundamental matrix is, and more importantly, we don't actually have to compute this bit in the end. All we're looking for is what this is, because you'll see how these answers are formulated. Whatever 2x1 matrix we get here, it will be multiplied by that fundamental matrix to give us that particular solution. So it's really just this thing that we're looking for. We can drop the phi of t that was sitting outside here. So phi of t is negative e to the negative t, e to the negative t, e to the 5t, 2 e to the 5t. Let's find the inverse of this. Well, phi inverse of t is 1 over the determinant of phi of t. That's negative 2 e to the 4t minus e to the 4t. So that's 1 over negative 3 e to the 4t. And then inside our matrix, we will switch the a and the d position. So 2 e to the 5t up here and negative e to the negative t. And we'll flip the sign on the b and the c positions. So negative e to the negative t and negative e to the 5t, like that. So now let's take this guy, and multiply it by this term here. And then we'll be able to integrate that and we will have our answer. Okay, but first off, let's factor this 1 over negative 3 e to the 4t into here. We will get negative 2 over 3 e to the t, 1/3 e to the negative 5t, 1/3 e to the negative 5t, and 1/3 e to the t, like that. And we can get rid of that right there. And then computing this ends up being pretty easy. We just get, let's see, negative 24 over 3. That gives us negative 8 e to the 2t. And then on the bottom we get 4 e to the negative 4t. And then finally, all we have to do is integrate this thing. We have the integral of this dt. That will give us another 2×1 matrix. 2×1 matrix with entries negative 4 e to the 2t. Yep, that works. And negative e to the negative 4t, like that. So our answer should be B. That seems to match what we have exactly. Okay, and we are out of here. I'm sorry that some of the explanations on here were a little lackluster. The discrepancies between the MA 266 curriculum and the 262 curriculum is kind of showing here a little bit. But hopefully this was helpful wherever you needed it.